Hello everyone, I am Sambaran Bandyopadhyay from IBM Research AI and Indian Institute of Science, Bangalore. I will be presenting our work on hypergraph attention isomorphism network by learning line graph expansion. This is a joint work with Kishalay and Professor Murthy from IISc. This slide is to motivate the use of hypergraphs to capture higher order relationships. Conventionally, most of the networks are represented in the form of a simple graph where an edge can connect only two nodes. But if you consider real-world applications such as co-authorship network, co-citation network, chemical reaction, email communication networks, relationships are complex and go beyond pairwise associations. A more flexible and natural way to model such complex relationships is using hypergraphs. For example, if you consider a co-authorship network, a research paper can be co-authored by more than two authors. Similarly, in a citation network, a research paper might cite more than two papers. So in those cases, we need higher order relationships. Hypergraphs are introduced to model such complex relationships among the real-world entities in a graph structure. In a hypergraph, each edge may connect more than two nodes, so an hyperedge is essentially denoted by a subset of nodes rather than just a pair. So this is in contrast to a simple graph where an edge can connect exactly two nodes. So this is an example of a hypergraph. It has 7 nodes labeled as V1 to V7. It has 4 hyper edges labeled as E1 to E4, where E1 connects 3 nodes V1, V2 and V3. E2 connects only 2 nodes V2 and V3. E3 connects again 3 nodes V3, V5 and V6. E4 connects only one node V4. Here we define our problem statement and introduce necessary notations. So a hypergraph can be denoted as VE, where V is the set of hypernodes with E is the set of hyperedges. Each hypernode V is associated with a f-dimensional feature vector xv, and this forms a feature matrix capital X, which is of dimension V times f. So for example, if we consider a citation network where each hypernode is a research paper, this feature vector can be considered as the set of textual information present in each paper. We are using it for hypernode classification in a semi-supervised way. So we assume to know the label of a subset of nodes Vs. The incidence matrix of this hypergraph can be denoted as H. It's of dimension V times E. So if some hypernode V belongs to a hyperedge E, the corresponding entry of the incidence matrix will be 1, otherwise it will be 0. Hypernode diagonal degree matrix of the hypergraph is denoted as dV, where each diagonal element dVii contains the degree of that hypernode. Similarly, hyperedge diagonal degree matrix is denoted as dE. The goal of this work is to develop a novel graph neural network which can operate on hypergraphs even with varying hyperedge sizes and generate hypernode embeddings. We want to train the network on semi-supervised hypernode classification. This amounts to learning a function f which can assign a label to each hypernode in the hypergraph. So here we propose HAIN, which is an abbreviation of Hypernode Attention Isomorphism Network. This is a novel graph neural network algorithm for hypergraphs exploiting the concept of line graph in hypergraph. We'll discuss about HAIN in the next few slides. So first we introduce the concept of line graph of a simple graph. So given a simple graph having 4 nodes, you can see that in the corresponding line graph, each edge of the simple graph is represented as a node. Now 2 nodes in the line graph will be connected by an edge if the corresponding 2 edges in the simple graph shares a common node. So that's how we form this line graph of this given simple graph. Now the concept of line graph for hypergraph is also quite similar. So for each hyper edge, we create a node in the line graph, and 2 nodes are connected by an edge in the line graph if the corresponding 2 hyper edges in the given hypergraph shares at least one common hypernode. However, computation of line graph of a hypergraph needs order of e square v time. So this is quite significant and large. So if we want to build the line graph explicitly, the approach will not be scalable. So our solution Hein uses a simple trick to avoid the explicit computation of the line graph. Hein also learns the edge importance through an attention mechanism. So we'll discuss about both these points in the next slide. So this slide gives the fundamental working principle of Hein. To start it, we assume to form the line graph explicitly, but at the end we'll see how to avoid the exact formulation. So given the incidence matrix H, the degree matrix dV, and the edge degree matrix dE, the line graph, the adjacency matrix of the line graph can be obtained using this equation. So the adjacency matrix of the line graph is clearly of dimension E times E. Then we introduce this message passing mechanism in the line graph of the hypergraph. So as you can see that HTX, so H is again the incidence matrix of the hypergraph, X is the hypernode feature matrix. So HTX can be considered as the hyper edge feature matrix. So when this is multiplied with AL, this can be considered as having message or passing the messages in the line graph of the hypergraph. This concept, we introduce this variable epsilon based on a graph isomorphism network or GIN. So this whole process is equivalent to converting the given hypergraph to its line graph, do the message passing in the line graph, and then converting features back to the hypergraph. However, here in step 2, we are using the weights of the line graph as they are, or in other words, we are not learning the weights. So to tackle that, we introduce this self-attention layer. So the purpose of this self-attention layer is to learn the weights of the line graph. So here theta attention theta ATTL is the attention vector of Hein for the Lth layer. So this is a trainable vector. So now if we expand AL and XL in this equation, we'll get the final update rule of Hein. So interestingly, if you solve this equation, or if you solve this matrix multiplication from right to left order, you can see that we don't really need to compute the expensive line graph in this equation. So by solving this equation from right to left order, Hein takes only order of VE time, which is much faster compared to the computation of only the line graph of the hypergraph, which needs order of E square V time. Thus Hein is quite scalable. So this shows the high-level architecture of the Lth layer of Hain. So given the hypergraph along with the hypernode features, first we implicitly compute the line graph of the hypergraph. Then the self-attention mechanism is used to learn the edge weights of the line graph. Finally, we use a graph isomorphism network on the line graph. But as I said before, this is just for the purpose of illustration, because in actually we are not forming the line graph explicitly in Hain. Okay, so now I will discuss about the experimental setup and the results of Hain. So we used four popularly used graph datasets. So first three, Cora, SiteShare, PubMed are co-citation networks, and DBLP is a co-authorship network. We have mentioned the number of hypernodes, hyper edges in each of these datasets. So we also conduct a model ablation study to understand the efficiency of different components of Hain. So first we consider star gene. So here we convert the given hypergraph to a simple graph by star expansion and use graph isomorphism network on that expanded simple graph. The second model as part of model ablation study is click GIN, where we use a click expansion to convert the given hypergraph to a simple graph and then use gene on top of that. Static Hain is basically Hain, but we didn't use the self-attention mechanism in the Hain, and we refer that model as static Hain. So here are the results for hypernode classification. So as you can see that we have used a diverse set of baseline algorithms. So here confidence interval based method MLP and MLP plus HLR, these are conventional approaches on hypergraphs. HGNN, DHGNN and HyperGCN along with its variants are state-of-the-art hypergraph neural networks. Hain is our proposed algorithm, and star gene, click gene and static Hain are three model variants of Hain studied as part of model ablation study. So as you can see that for all of these datasets, Hain is able to achieve state-of-the-art performance with for some of them the performance gap with respect to based of the baseline algorithm is also quite significant. We can also see that Hain is able to outperform its model variants for all the cases, for all the datasets, which shows the importance of different components of Hain. We do some analysis on the training. So here we see how the training loss converges with different epochs of Hain. And in this plot we have we have shown the training time of Hain on different datasets along with its variants. So Hain is not computationally expensive compared to its model variants. We also do some sensitivity analysis of Hain. So here we vary the training size and see the accuracy of Hain. You can see that when we increase the training size from 1% to 5%, there is a certain jump after the performance saturates. Similar observation can also be made when we see the accuracy with varying embedding dimensions. So here are the conclusions. So we proposed a novel graph neural network algorithm referred as Hain, which operates directly on the hypergraphs and can handle varying edge sizes. Hain implicitly formed a line graph from the hypergraph to make it computationally efficient. Hain uses an attention mechanism to learn hyperedge relationships. Hain shows promising results for hypernode classification, both in quality and computational time. Model ablation study shows the usefulness of each component of Hain through experiments. Thanks for attending this talk. Please feel free to ask questions during discussion. Thank you.